All right, so this is for Chapter 15. This is stellar remnants, white dwarfs, neutron stars, and black holes, which we started to talk about a little bit in Chapter 14. Of course, this chapter could be titled "The Death of Stars." All right, there's three ways that stars can die. By far and large, the vast majority of stars out there in the universe will end up as white dwarfs. More massive stars, that is, generally when we talk about massive stars, they're at least anywhere from about 10 times the mass. They can be as low as 8 times the mass of the sun or greater, 10 to 8 or more, right? So you remember, stars can be as massive as 30 times the mass of the sun. Anyhow, those massive stars become either neutron stars or black holes, and they're also collectively known as compact stars. Well, all three of them actually. And in these compact stars, the matter has been crushed to an unusual state. We'll discuss that in much more detail. For example, a very typical thing that people in astronomy like to talk about is if you could get like a small little like a little cube, like an ice cube, like it says here, an ice cube size. So the size of white dwarf material would weigh literally more than 16 tons. So you don't find any white dwarf material on the Earth. And of course, neutron star material would be even more massive. And then, of course, black holes, well, they're not even, they exist in the sense that they offer gravitation, but it's not like you can grab a scoop of black hole material, because it's reached the point where space and time have curved in on itself. All right. Anyhow, we'll talk about that in more detail. This, of course, is a nebula that remains after after a supernova explosion. Sometimes they can be more symmetrical. This one, I think this one's called the Veil Nebula, if I remember correctly. Anyhow, the name doesn't matter. This one is not evenly distributed. All right, so there's an actual picture of a white dwarf. These things were discovered. Let's see, it was almost at least 200 years ago. In fact, the very first one. This might be actually the first. I don't know if this is the very first one. Anyhow, the very first one was discovered around the bright star, the brightest star in the night sky, called Sirius, and so the bright star Sirius turned out when we had telescopes with enough technology, we could actually see a small object that was in orbit around Sirius. And it turned out that it had an incredibly high temperature. Of course, we used Wien's law to figure out the temperature. The temperature of this thing was more than 25,000 Kelvin. Remind you that the sun, our sun, is at about the surface temperature of the sun is about 6,000 Kelvin. So, the only way that you can produce something with this incredible amount of temperature in such a small amount of luminosity is if it's really small, and so that's how it gets its name, a white dwarf. And if you remember, in chapter 13, we had that tool for measuring this. Using luminosity and temperature, we could calculate the size of stars, and when you calculate the size of a white dwarf, it turns out to be about the size of the Earth, or smaller in some cases. Or sometimes a little bit larger too, but around the size of the Earth. All right, so what a white dwarf is really what remains from a dying low mass star, right? So this is really what happens long after the planetary nebula has gone off into space in all directions, and you just have this it's kind of like an ember of in a fire, although of course it's not fire, but it's just cooling, and it takes incredibly. In fact, in some cases, we've calculated that it'll take like 100 billion years for these things to cool down to around the same temperature as space. So it's like, if you think about it, some people like to compare it to senior citizens, right? Senior citizens have accumulated. You think of it like in terms of money, right? Senior citizens have been around for longer. They've accumulated more wealth, generally than like the younger population, on average. And so what the white dwarf is doing, it's like a senior citizen, and but with energy, with heat. And that heat is just being released out into the universe. Again, takes billions upon billions of years for these things to cool down. All right, so this is just showing you. Remember, this is the variable star part. When the star is a variable star. And then it loses its outer shell. And actually, this can happen more than once. And this is the planetary nebula that's escaping out into space. And so long after this planetary nebula phase, what remains is this tiny little dead star. Remember, what we mean by a dead star is that there is no fusion taking place, none whatsoever. It's not fusing carbon. It's not fusing oxygen. It's fused all the elements that a low mass star can possibly fuse, and some of that material does end up traveling out into space in the planetary nebula phase of these white dwarfs. But so what remains is just this tiny little mass. Like I said, roughly the size of the Earth, give or take, and with at least the mass of the Sun, and sometimes less than the mass of the Sun. But all right, so now you might say, all right, well, what is it? Remember, a regular star, going back one chapter, a regular star has a balance between the inward pull of gravity, which is always there, but there's an outward pressure due to fusion, the conversion of hydrogen into helium. But in this particular case, it's not fusion anymore because fusion has ceased. And so what it turns out that there's this process. It's a quantum mechanical process called electron degeneracy pressure. That's just its name. Okay. It just basically says that two electrons can't occupy the same quantum space, the same quantum state at the same time, and so the electrons resist being squeezed to a certain extent. That they will resist, and the amount that they can resist is called the Chandrasekhar limit. And what I mean by that is the amount of mass that the electrons will push back is called the Chandrasekhar limit. This was a brilliant physicist who, I think he did this in the 1950s or 60s. I can't remember exactly when, but he worked out the mathematical details of this, and it turns out the Chandrasekhar limit. Let's see, do they show it? It should be. Oh, there it is. So this is the maximum that a low mass star can support. So which is 1.4 times the mass of the Sun. So that's what's called the Chandrasekhar limit. Okay, anything basically, let's go back to after the planetary nebula phase. If there's 1.4 times the mass of the sun or less, then electrons can resist the star being compressed any further. Okay, the electron degeneracy pressure offers resistance to the inward force of gravitation, and then the star stabilizes and just loses heat. Right, it's no longer fusing. There's no fuel. These things are incredibly dense, in the order of millions of grams per cubic centimeter. So this is, by far much more dense than anything humans can create in our laboratories. All right. So this is just a little thing about this idea of electron degeneracy pressure. It comes from the Pauli exclusion principle, which is a principle from quantum mechanics. You might have heard that if you took any chemistry. So that's what this degeneracy pressure is. Just remember that's what it is, and that as long as you have 1.4 times the mass of the sun or less, that will resist being squeezed any further. Okay, by electron degeneracy pressure, which of course is an outward pressure. All right, but you might say, well, wait a second. What if there is more than 1.4 times the mass of the sun that's remaining? All right, so like with more massive stars, for example. We'll get to that. Okay, so we're heading in that direction. One of the things that we notice with these white dwarfs is there is what's called a gravitational redshift. So the light that leaves the white dwarf will shift. It'll do a redshift just because of gravity, because the gravity is so strong near these, and that's actually going to turn out to be true for neutron stars as well. We're about to get to them. All right, so there is this this redshift to be aware of. All right, now sometimes a white dwarf can get a second chance, a second hurrah, if you will. And that happens when there is the white dwarf is in a binary system where its companion star is still on the main sequence, let's say. And so what happens is if the white dwarf is close enough to its companion star, now some of them are too far apart for this to ever happen, but if it's close enough, it can actually steal some of the material off of the main sequence star, and that material forms a disk around the white dwarf, and then will literally fall onto the surface of the white dwarf. And that's basically a nuclear bomb waiting to go off. It's hydrogen. It's just raw hydrogen, and it starts heating up and heating up and heating up, and more of this hydrogen will build, and then this thing will flash, and that's what we call a nova. Or back in the old days, people used to call this a nova. It actually has a more technical name now, but that's what people used to call it. All right, so there's the word nova, and nova just means new star. That's all it is. This is because all of a sudden one of these binary systems will ignite, and it's not nearly as bright as a supernova, for example. Although the modern terminology is it's actually it's called a type 1A supernova. Anyhow, so in the old days it was just called a nova. Now it's a type 1A supernova. All right, but it's not like the supernova of a of a